Director of System Planning. We have a pretty good agenda this afternoon for you guys. So I would like to just welcome you to this workshop. It was in concept. We put this together in fairly short order, I think over the course of about 3 weeks. But I think it's very timely. I took some statistics just to kind of introduce kind of where we're at. With SPP's footprint, we had over 7 gigawatts of wind installed in marketplace in 2014. And at the time, we thought that was a lot. We've exceeded 27 gigs registered. Not all of them are commercial yet, but 26 gigs or more are commercial, 27 gigs installed or registered. And so that's about quadruple. We're about 400%, just about, in 7 years' time in the amount of wind resources we have. Over 13,000 individual turbines. I don't have the statistic on how many registered wind farms themselves. We have some fairly large ones. So yeah, we've been integrating wind for quite some time. We're fairly good at it. We've exceeded 82%. I think our peak wind serving load was 84%, right on the dot, just a week ago in May. And I think at the same time, we were 87.5% renewables. That was hydro, since usually our wind peaks are always at night, so solar doesn't contribute. And now we're kind of asking ourselves, what will it take to go to 90%? What will it take to go to 100%? We still have a lot of wind in the queue. I think, at least from my personal thought, is that solar is going to be our next frontier. We only have a little bit of solar on the wholesale electric system and the bulk electric system, and that amounts to about 215 megawatts of solar. So we're pretty new, I guess, from an RTO perspective on the solar front. We have upwards of 10 gigawatts of electric storage resources in our GIQ. So from an inverter-based resources perspective, we have a lot of IBR installed, and we have a lot more coming. And you know, some of the statistics you probably have seen, we exceeded winds exceeded coal for energy last year in 2020, just barely, but it became the #1 resource for SPP. And so we're embracing it. Wind is definitely here to stay. But with inverter-based resources comes a new challenges. It's not what we've traditionally planned for or operated for. As good as I believe we are as a membership and SPP as a footprint at managing wind, we've installed great forecasts and great policies and tools reliably. There's much more to learn and much more technical aspects to IBRs, what the challenges might be with this wholesale regional fuel mix change that we're seeing and probably will continue to see for a number of decades. And so I think this is pretty timely. It's geared towards educating ourselves on not only the challenges, but also potential solutions that we need to be looking at. And so with that, that's pretty much all I have to say. I'll hand it over to Debbie, and then we can get started on the overview of the agenda, and look forward to educating myself. Thank you.
Thanks so much, Casey. So I'm really happy to also welcome all of you to this SPP E-Cig joint workshop on interconnection of inverter-based resources and weak grids. As Casey said, this is a really timely topic as we start to put more and more inverter-based resources on the system, and we have less system strength on the system. How we interconnect these resources, models, processes, the planning needs to change. And as the equipment also changes, there's a lot that we're learning these days from places like, Texas and Australia, where some of this is really on the cutting edge. And we're going to talk about that today. So just real quick about E-Cig, Energy Systems Integration Group. We're a member-driven nonprofit. We work on technical challenges on transforming energy systems. So we work on variable renewables, energy systems integration. We just finished a spring workshop. We're about to start a forecasting and markets workshop, and that's all free. You can go to this website to view that. We're also part of the Global Power System Transformation Consortium, and there we're working with some of the bleeding edge system operators on issues around things like high penetrations of inverter-based resources. So I'm really excited today because we've got some fantastic speakers. We've got really lucky to get really some of the leading experts in this topic to talk to you today. So Nick Miller from HickoryLedge, who retired from GE after 3/8 of a century of work there on these topics and more. And I'm not going to go into great detail on everyone's bio, but Nick does quite a huge amount of work in this area, and I'm sure a lot of you are already familiar with him. Then Jason McDowell from GE, who's Senior Director of Technology, Strategy, and Policy, who also leads our reliability working group. And right now is in the process of, we're putting together a big paper on grid forming inverters. And then Sebastian Achilles, who's a manager of power systems operations and planning at GE Energy Consulting, who's personally done quite a bit of these interconnection studies and has the practice on that side as well as on the inverter side and what needs to go into new inverter design to make these systems work in very weak systems. And then last but not least, Fred Huang from ERCOT, who's manager of system planning and responsible for regional planning and dynamic studies, and we'll talk about some of their experiences in ERCOT. So the way this is going to work is that we've got a lot of presentations, and we're going to take real quick clarification questions and answers through the chat functions. There's a little chat button at the bottom right of your screen. You can put questions in there, and we'll try to get to as many of those as we can during after each talk. But at the end of the 4 talks, we're going to allow people to unmute themselves. So if you'll raise your hand, you can unmute yourself and ask questions, and we can have more of a discussion verbally at the end. One last thing is that it's being recorded, so other people can, who weren't able to participate today, can follow along with us. So with that, I'm going to turn this over to Nick, who's going to start with export stability and weak grids. So take it away, Nick.
All right, thanks, Debbie, Casey, and good to see good to hear everybody. And you can tell that my bio is correct because as soon as you retire, you stop buying clothes, and so my biographic picture has the same yellow shirt on that I'm wearing today. That's proof that I'm retired. I'm going to do a quick high-level look at stability in weak grids with particular view towards getting power out from inverter-based resources to the grid. This is necessarily quite a shallow look, but it sets the frame up for the 3 speakers who are experts after me. So with that, oh, wrong button. We're going to look at synchronization issues. So it's a real simple thing, and then some of the limitations of the model, what the system looks like when it's weak, and what some of the tools in the toolbox are. And as I said, these will all set you up for the balance of the afternoon. So I'm going to start with a couple slides of super basic stuff, for which I apologize if it's too basic, but it's quite useful to set the stage for some of the things that are different and limitations. If you don't know, hopefully it gets us all on the same page. So first and foremost, wind, solar, PV, and batteries are all inverter-based resources, and they have fundamentally different behavior than synchronous generators. Today's reality is that all of those resources, all the wind and solar that you have on the grid and will have in the immediate future, are grid following. We'll talk about what that means. And then somewhere down the road, to address some of the concerns that Casey and the other speakers will bring up, we are going to be at least starting to glance at so-called grid forming inverters. So I put this cartoon together for people that get bogged down or sensibly confused about all the block diagrams and other things. This is supposed to be a simple drawing. In the end, it's really not. But as for understanding, you have to remember that we actually live in a 60 hertz world where there's hopefully sinusoidal voltages, and grid following inverters depend on that sinusoidal voltage. So upstream, and I'm not going to talk much about that today, we have regulators that are trying to figure out how much active power to push into the system from the wind, solar, or battery, and how much reactive power is necessary to maintain voltage. So we have closed loop regulators for those two red and purple functions that look like straight lines in time. We're used to phasor quantity. So this is all steady state in this drawing. In order to accomplish that, we have two components of current. So our devices are current injection devices. We inject active current, which is sinusoidally in phase with the voltage to get watts, and we inject reactive current, which is sinusoidally 90 degrees out of phase to get VARs. Those are the two curves that are in the different shades of orange. Big piece of this puzzle is that those currents, first of all, are added together. There's only a single current, which is that dotted orange curve, and it has a known phase relationship to the voltage that gives me that summation. The phase lock loop or some other mechanism is the device that figures out where that sinusoid is. So that is the basic control of all inverters, all grid following inverters. Look at the voltage, figure out what current to inject at what phase angle. Doesn't get any simpler than that. The problem is that sinusoidal phasor, the blue in this figure, moves. And for example, in the very simple example in this drawing, when the frequency drops below 60 hertz, that sinusoid drifts out. And if I use the same current as I had in the previous figure and don't account for the fact that the sinusoid has moved, the phase relationship of the orange to the gray after a few cycles, this is an extreme change in frequency, incidentally, in this drawing, it's doing the wrong thing. The current relationship to the voltage is wrong. We don't get the watts we want. We don't get the VARs we want, and the outcome is not what we want. So the mission of figuring out where that sinusoid is and figuring it out with high fidelity and quickly is the challenge of design of inverters in power systems. So you see that moving, that's when the system is moving. But the other piece of the puzzle is that the very act of injecting current causes the voltage that can be observed by the inverter to move. That's what my little finger cartoon is here. So by injecting current, I actually cause the voltage to move. So if my current injection is sufficiently violent, I'll use the word violent, then the voltage moves somewhere where the device that's injecting the current gets confused and can't figure out where the voltage actually is. That is a cartoon version of an instability. The movement of that voltage is easier. It moves more for a given amount of current as the grid gets weaker. So if the grid is too weak, the interaction between the current injected and the motion of the voltage becomes ill-mannered. And that's what we're worrying about in weak grids. So sorry for making that so cartoonish, but that sort of lays out the problem. Of course, in practice, sinusoids are distorted. They jump around. On the right here are a couple of figures for simulations of different kinds of faults. You see a balanced three-phase fault at the top, which is kind of sinusoidal after about a cycle. You see two other kinds of faults on the right, and you see big differences between the phases, big jumps in the phase angles. And the bottom line is that you can't make things too fast because the regulator can't figure out where the world is that it's trying to track. So again, that's a cartoon version of the limitations of how aggressive you could make the control, because it can't figure out where it is and it will move out from underneath you. So the experts after me will talk in quite a bit more detail about some of the things that we do to manage that. So here you are on this call, and many of you on the call are planners that are looking at trying to design a system with ever more of these inverter-based resources, which have that behavior, which is really, really different than a synchronous machine. And this shopping list on this page sort of lays out some of the things that can go wrong with stability models. So one of the things that you see is that they crash. You start pushing the model to higher and higher levels of stress and more IBRs, and that is problematic for the algorithm solvers. The differential algebraic equations get ill-mannered, and one of the things that you look for is, oh, the simulation crash, the system is unstable. Well, that's actually a relatively poor metric. Yes, it's a yellow flag, but no, it's not firm evidence of instability. Another thing that happens is that the phasor models that are in your stability runs are limited with the expectation that the grid is algebraic. So anything that's moving faster than 3-5 hertz isn't very meaningful for phasor analysis, and people will debate what that upper limit is, but really fast things can't be captured. So if you start seeing your simulations oscillating at 10 hertz or 20 hertz, it says something's wrong, but it doesn't really tell you anything else beyond that. And looking at oscillations, even the ones that we're accustomed to looking at, like the stuff that's addressed by power system stabilizers, the actual physics that's driving those oscillations may be quite different than it was historically in synchronous machine dominated systems. So the ability of these tools to capture the frequency of those oscillations and to get the pieces right is actually is pushing the envelope. One of the worst things that can happen, and we constantly we as an industry are working to make sure this doesn't happen, is that phasor type models can miss problems that you might see with more detailed representation. So stability models that ignore, for example, that tracking of the voltage, whether it's by PLL or some other mechanism, might conclude that things are stable when indeed they aren't. That's one of the scariest things for system planners, and one of the risks is associated with that tracking, i.e., the PLL. So the upshot, and it won't be news to most people on the call, is that sometimes EMT types of magnetic transient analysis is needed, where all three of those phases are represented in all their glorious physics. But that in itself is quite difficult to get right. It's hard to have adequate size models, and it's hard to get, there's a lot of things that can go wrong. So the opportunity to have very expensive, very complicated simulations that are meaningful is quite high with EMT simulations. So what can go wrong in real life? I have a single example here, not necessarily intended to scare you, but consciousness raising. This is a blackout that occurred in the UK that was driven by a wind plant. And I won't give you all the gory details, but it was a gigantic plant, 800 megawatts, to be 1600 megawatts, connected to the AC system. They had a small event, and the plant misbehaved. It did not understand that the event that occurred had dropped the system's strength, driven in the direction of being weaker. And what you see here are traces. Those are oscillations as it flogged for a couple a couple of cycles of this instability and then tripped. And the trip took out some other generation, and the biggest nasty was that it took out some rail customers that were not under the control of National Grid, and the rails during rush hour were shut down for many hours, and people were enraged by that. That's all this kind of scary thing. They would not have probably caught this even had they been looking for it. And what happened was, during the course of commissioning this plant, they had off-the-shelf controls in the wind plant. They hadn't set up the controls for weak grid. And they saw this happen. They went out, and basically within 24 hours, they had the problem, the risk removed by having the right controls in place. So scary, cautionary, but also in this particular case, it's something that they could have seen coming had they been watching, and the OEMs were quite capable of making the plant behave itself properly. So I have a quick example of work that we've done recently. I've done with my friend Matt Richwine at Telos. This is work that was funded by Grid Lab, and we did a seminar. The link to the seminar is on the right hand down at the bottom if you want to go through the detail. But we were looking at the problem of exporting power, not unlike, at least in cartoon form, what you're doing in SPP, where you have big plants that are relatively far from the electrical load, where you're trying to push power. In your case, you're often trying to push the power to the east. There's a very simple topology. There's a lot of stuff that goes around this, but I wanted to put this example up because this is one of the challenges that is kind of at the top of the list for SPP. There's a lot of concern about grid frequency, whatever, but the reality is you're in the Eastern Interconnection. It's can you keep pieces of SPP stuck to the rest of the Eastern Interconnection successfully is the first and foremost stability issue. So this eye chart here, I call this a stoplight chart. From left to right are 3 columns of progressively weaker systems. So I got what I've called soft grid, because it's by no means stiff. This is short circuit ratio of 2.2. Fred's going to talk about that more later. The middle is what today would be called very weak for grid following inverters, and on the right is weak as the short circuit ratio is approaching 1. And the top row is for a current state-of-the-art grid following inverter, so best in class of what you've got on your system. And you see, for even the pretty soft grid on the left, it behaves well, and the top center, it makes it through this event, but kind of ugly, and it's a violation of NERC voltage criteria in that case, so it's not truly stable. And then on the right, you see it flogging at about 1 hertz and finally failing. In the middle is all of the things being identically equal with a synchronous machine, and those wiggles will look quite familiar to you. You see the damping gets worse, the post-fault recovery voltage is uglier in the yellow case, also a violation of criteria. And then on the right, you have loss of synchronism, and that's a classic pole slipping case on the right. Across the bottom, and I'm not going to talk about it much more, but this is with a present state-of-the-art commercial grid forming inverter. This happens to be for solar, not wind, but this is a manufacturer's model. And without going into it too much detail, it's stable all the way across, including down to very weak. So was the point of that particular investigation. It gives you a little glimpse, not a complete story glimpse into a future. Those results are summarized on this chart. And the one thing I want you to learn from this is as the system gets stronger or weaker. So just again to emphasize, the left to right on the previous chart is top to bottom on these 3 different figures. So the top of the top on the y-axis of each of these 3 is a relatively stiff system. Stronger grid means lower impedance, higher short circuit ratio. I'm not going to get into the numbers of that if you're not familiar, but 2.3, which is the top across these charts, is still a relatively soft grid. As we get down into the yellow area, the system is what would today be called weak, and in the red is extremely weak. So those color codings on this are the regime where, for that simple little model, the system is stable or unstable. Lots of details. I don't expect you to be able to see the numbers, but there's a trend that's quite important and debatable how universal it is. But the x-axis on this plot is the fault duration. So those of you that have spent your life looking at synchronous machine stability are used to the center plot. Whereas the fault gets longer, the system gets less stable. So it's less stable for a stiffer and stiffer system. And if the fault's long enough, it doesn't matter how stiff the system is, it's unstable. So there's this curved case going up to the right that is progressively less stable. For the inverter-based resources, that duration of the fault is relatively unimportant. It's all about system strength and control stability. And then finally, on the right, and I won't belabor that, is for this particular set of assumptions, and I got to emphasize that, this snapshot, the grid forming inverters are significantly more stable and relatively insensitive to duration. So let me wrap up.
There's 4 more minutes, Nick.
Okay. Yeah, I can get there, I think. So there's a bunch of tools in your toolboxes that you're accustomed to that are intended to make the system more stable and give you the ability to push more power or handle more violent events. The industry has made grid following inverters spectacularly more stable. So the stuff that's being made by the big OEMs today can get you down into those short circuit ratios below 2, which was almost impossible a few years ago. So this trend is expected to continue, but there is some limitations on it. You can always put more wires in the air, and you can add system stiffness by the use of other synchronous devices, specifically condensers. I had some examples of that, but it's a little long to bring it in there. Condensers are a two-edged sword. They can screw up, they can introduce other dynamics, but while they make the system stiffer. And then finally, as you guys have just hosted fairly recently, there's a bunch of grid enhancing technologies that help mitigate those stability issues. So in summary, I've put a couple of examples, a couple of things that are a little scary, and I want to walk away with this continuum idea so that you're not looking down the barrel of moving to a world that is so challenging that you don't know how to make it work, because you don't get there in one step. And quite honestly, SPP has done a spectacular job of regularly moving across this spectrum on the left of relatively easy, plug the stuff in, do your due diligence, it works okay, to moderately stressed systems, which are kind of in the middle of this thing. Again, you do that well, you can use your PSSE stability tools as long as you are very careful to define the system and look for all of the challenges, look for the complexity of interaction between multiple plants and other resources. As we move to really quite weak systems, we're getting to the point where grid following devices are going to be quite tricky to get right, that your PSSE, your stability models, per my point early on in the lecture, start to not have the fidelity necessary to do all your engineering. They may have to be augmented by using EMT type tools, which I call PSCAD here, it should have been consistent, or there's other complexities. And then finally, as we start to go to extremely weak, under short circuit ratio of 1, down to including 100% zero synchronous stuff, you're a long ways from having to do that in normal life still, because you're connected to the Eastern Interconnection, but questions of whether or not an island can be sustained with just inverters. Those are very specialized, and the technology is getting there, but you can't figure out how to make that work with just off-the-shelf tools. So the world keeps getting more interesting as we go from left to right, but it doesn't do it stepwise. So with that, I think I just about got it on time. And I guess I could take one or two clarifying questions by chat, or we can get on to the next speaker.
Sure. Here, I'll just, there was a question that came in, and I think you did sort of go over this, but it asked if you could define soft, marginal, and weak grids. The grid lab piece.
Yeah, I think I probably answered that, at least insofar as it makes sense to answer it at this point. Both Sebastian and Fred are going to till that ground a little bit deeper, so I'll pass on saying more.
Excellent. All right. Thank you so much, Nick.
All right.
So we're next going to pass the ball over to Jason McDowell from GE, who's going to talk about an overview of interconnections. So if we can.
Great. Thank you, Debbie. Thanks, Nick. Would also like to say thank you to all of you that are participating today. It's great to be with you here, especially on such an important subject, particularly around integration and how our world is changing. And I think that's a lot of the complexity that we're seeing now, is that a lot of things are changing regarding integration of more inverter-based resources and how we assess the risk. So that's what I'd like to talk over the next 15 minutes about or so. And then pass it over to Sebastian and Fred to talk more deeply about some of the phenomenon and how particularly the controls and the models are evolving. So Nick talked a lot about this, and I don't want to dwell on it, but more or less how weak is weak, how strong is strong. Generally, the weak grids we look at in terms of their the fluctuation that happens in terms of voltage and current relative to many plants influencing the voltage and current by injecting current, by injecting real and reactive power during a host of different system operating conditions. So this is what we're looking at. And as the grid gets weaker, it gets slipperier, things are moving around more, and we have to look at different system operating conditions. So the name of the game is to identify the risky conditions. And those risky conditions are above and beyond the standard planning conditions, likely at peak load, at light load. It's more going to be looking at system conditions when you have high penetration of inverter-based resources, those hours that are going to, that are really having high penetration and have risk of control interactions with inverter-based resources, and also other system operating conditions when you have an outage and you have high shares of inverter-based resources. So traditionally, the planning software, PSSE, the fundamental frequency tools, have been put in place to look at transient stability, oscillatory stability, electromechanical interactions, and those are there traditionally to look at how the system stays together relative to rotor angle stability and the like. But more control stability that we talk about related to inverter-based resources, as Nick pointed out, need to be assessed with more detailed models, electromagnetic transient models like Psk. And more today, to understand the capability of the equipment and what might go wrong, EMT models are being used more and more. And the other trend is to see that they're being used for longer time durations as well, to look at the many hierarchies of control that would need to coordinate and be interoperable with one another. So there's one train of thought that says, why don't we use EMTP models for everything, right? And evaluate all of our risk with very detailed transience models. But obviously that has the challenge of being very computationally intensive, being very data intensive, being very intensive in terms of getting all the models to work together. And so the name of the game here is to understand when we use EMT models, how we use EMT models in concert with the traditional stability models to assess the transient stability and oscillatory stability, and make decisions as to how to mitigate risk around weak grids. So some of the big challenges we've had in the past, and I want to point out that the simulation tools continue to evolve. The models continue to evolve. The fundamental frequency models that look at positive sequence behavior continue to get better and better, but they still don't have the fidelity of the controls in detail to look at some of the characteristics that Nick pointed out and that we're going to talk more about later to analyze the overall risk of control interaction and control instability. In some cases, the stability models, well, they don't represent all of the capability of protection and control and in sufficient detail, and may either be not representing all of the conditions that will actually happen and will be over optimistic and not show the problems that may occur with control interaction because they simply don't have the fidelity, or they may indicate where tripping may occur in the model where it actually is just fine. It depends on the assumptions in the model that you use. So when do we trust the stability models, and when do we need to go deeper and look at the EMT model evaluation for overall risk? One of the metrics that we've used and continue to use and evolve over time is looking at short circuit ratio, as Nick pointed out. And this has been institutionalized in many areas. NERC back in 2017 wrote a reliability guideline that calls out the different ratios. Certainly there's a lot of experience in Texas with some of these ratios, and Fred's going to talk a little bit more about that. And other groups like CGRE have been looking at these ratios as well to understand and identify the limitations of the stability models in PSSE and PSLF, and when we might need to look a little bit deeper because those capabilities are not, and the fidelity is not in the stability models to predict this control interaction. So the first one is the short circuit ratio of the point of interconnection looking at one plant. This honestly really is not the best one to use in most cases because it only looks at one plant relative to the short circuit capability. But when you really need to look at the interaction of an area with many plants, looking at the capability of composite ratio or weighted short circuit ratio, as we see there, is a better metric. It looks at the overall capability of the short circuit strength coming from non-inverter-based resources being fed into a particular point relative to either the power being injected into the grid by inverter-based resources or the base capacity of inverter-based resources, as you see in the composite ratio. And that will give an indication relatively of how much inverter-based resource do you have in a particular area, how weak is it, and what are the limitations of the stability models, and when you might need to go deeper in using the transient models. Traditionally, if that ratio was below a ratio of about 3, then we said, let's go deeper and look at doing the stability or the assessment rather with the EMT models. That continues to get lower and lower. And as the models get better, they will ultimately be allowed to go a little bit lower, let's say to 2 or 1. Manufacturers and those that are modeling their stability in the stability programs are continually lowering that threshold. So the best practice is to contact the manufacturers and get an idea of where and when those stability models are at their limit, and then go back to understanding when we might need to use the EMT models. So a lot more on that. We're going to talk about that more later, but just to wrap up.
It's Jason.
Thanks. Perfect, Debbie. We'll wrap it up here in the next couple of minutes. So let's talk first about the plant level regulator interaction and coordination, and then we're going to dig more into the turbine level later on. So one of the issues is the plant level regulator coordination, where you have multiple plants together that will interact due to slight errors in PT measurement that will cause VARs to circulate from one plant to the other. You might experience circulating VARs to the point where you hit the limit and you have no VARs left to respond to system conditions when you have a grid event. Voltage droop is one of the ways to coordinate this and mitigate this, but without asking the question, what is out in the grid? Are there multiple plants around near me in my interconnection? And do I need to evaluate this control interaction at the plant level? And do I need voltage droop? That question should be asked right up front very early on. And additionally, fundamental frequency tools won't predict the interaction unless it's specifically modeled where we have a slight difference in either the measurement or the reference that will show this interaction. So the best practice is to make sure, the next slide, that we understand what's around us and from interconnection of one plant, and if there are multiple plants around, it's very likely that we will need to coordinate those multiple plants with voltage droop at the interconnection and at each plant control, and reflect that mitigation as early as possible in the models and as early as possible in the interconnection process as you're applying for a new plant to be connected. As well as testing the mitigation of the voltage droop is a very good practice, and assuring that the coordination of the controls are done adequately throughout the interconnection process, including the validation of the models, is going to be key. So with that, I'd like to wrap it up and ask for any questions if we have any quick questions, and if not, I'll hand it over to our next speaker.
So Jason, there was a couple of questions. One is that we're talking about this analysis primarily in terms of generators and interconnection. And this was when you were talking about the plant regulator coordination.
Right.
To what extent is this analysis also used in the transmission planning process?
Right. So as the models are put in place through the initial models that are given by a manufacturer and a generator owner, ultimately to test the viability or the system impact, as much as possible, trying to get that capability if voltage droop is needed, and it will be part of the overall plant interconnection. Getting that in the planning model upfront and looking at the capability is key to understanding the risk and how to mitigate it.
Excellent. There's another question. Can short circuit ratio be roughly estimated in a DC model? In other words, can you estimate short circuit ratio as a function of unit dispatch, commitment, and DC power flow?
That's a good question. Generally, short circuit ratio is based on the overall installed capacity of inverter-based resources relative to the amount of fault current that is provided by other resources that are non-inverter based. So to the degree that you can estimate the nameplate capacity of inverter-based resources to look at the overall capability, yes, but you're going to have to also understand the amount of short circuit capacity that comes from the balance of the grid to understand fundamentally the grid stiffness in the area. So I think the answer is partially yes, as long as you can have a handle on getting the short circuit capacity from the balance of the grid without inverter-based resources.
Oops. Okay, great. Thank you so much, Jason. With that, we're going to turn it over next to Sebastian Achilles from GE, who's going to talk about stability and low system strength applications. Sebastian, if you want to take it away.
Sure, thank you. So thanks for the opportunity to share our experiences. And congratulations to SPP for all the huge amount of IBRs that you have already connected. I hope that something I have to share is of interest to you. I imagine that you have to solve many problems to get to this point. Related to the question that was just said, probably the way I'm going to speak is also probably from the project interconnection experience. And if that you don't see that that's easy use for the transmission planning process, please feel free to elaborate with a question. I'm happy to get to think in those terms if I missed it. Okay, so this is the subjects I intend to go over. A little bit about, there are several controllers in an IBR plant, so which one is mostly affected by low system strength. I'll provide a few examples of IBR stability risk. We'll talk a little bit about the trade-off between speed of response of IBR plants and power system reliability. And then I'll talk about mitigation of stability issues. I think the general aspect of this is something that's well known to you, I imagine, based on all the experience that you've got. I'll describe a little bit of the project experience that I've seen from my current role in case relevant. And if there is time, I would add a few additional points on EMT models to what was already mentioned by Jason and Nick. So this is for a wind plant, but actually it's not too different for other plants. So in a wind plant, you have each wind turbine will have a converter control, a turbine control, and then typically the full plant will have a single plant controller that is taking measurements from the point of interconnection. So you have at least 3 types of controllers. If you look at solar or battery, it's not that different. In some cases, the converter control and this sort of prime mover related functions may be in the same controller. And in some cases, you may have 2 also for batteries and for PV. So this is quite representative of what you may find. So when you look at this, all of these controllers, and we talk about controlling stabilities, which one of these is the one that suffers the most or is more affected by system strength? So in principle, the converter control is the one that performs most of the actions during a fault behavior, a fault clearing, and is the one that has the faster control loops, is the one that has the synchronization logics that Nick was referring to. So the converter control is the one that is most affected. So the functions associated to the converter controls are the ones that are most affected. This converter control will basically receive commands from the plant level control and from the turbine control. I will try to respond to meet those commands of, for example, torque and reactive power, but then during a fault, it may depart from those commands in order to meet a particular performance requirement. The output of this converter control, actually could be a converter plus an additional card, would actually define the firing of the electronic devices. So this is the most affected controller. There are other controllers, though, that is important to consider. The turbine control is the one that would potentially also receive commands from the plant controller related to active power and will command the pitch control, and it will also command the torque to the converter control. The plant level control will typically try to control, for example, voltage at the POI or reactive power at the POI and frequency or active power at the POI. I imagine you have heard about this before, and will command the other controllers. So as I mentioned, the converter control is that it tends to be most affected with grid strength. And the plant level controller, particularly the voltage control, may also be affected, but it's not so involving to solve. Those are relatively simple problems to solve. Now, how does a vendor come up with the settings and configuration for a converter control? If we know we can have a weak rate, why isn't that just already configured for a weak rate? And we're done with this problem. So when you look at design processes for converter controls in wind turbines or inverter controls in a PV, as they are typically called, you see a number of things. One is these are short product cycles, so a product is good for 1, 2, 3 years. Maybe one is too short. Let's say 2, 3 years. So in 2, 3 years, you're going to be doing a new product. So you cannot be designing this product for 10 years because the product is going to be good for 3. The other aspect is that at the time of designing the product, you don't really know the projects that this product will be applied to. So the products are typically designed or fundamentally designed ahead of the project. So the team that is designing the controls and coming up with parameters for these control loops don't have the specific of each product. And if you think in terms of how massive this business is, so a turbine will be probably sold, I don't know, a vendor may be selling 3,000 turbines in a year, let's say 100 wind plants in a year. The team that is designing the converter control settings for the product before it's available is not looking at each of those, right? So the way this is handled in the product design is by looking at ranges of system conditions. And as you can imagine by now, there is quite a bit of consideration for weak grid conditions. Now, you can get to a particular level of weak grid in different ways. So you can come up with different grid topologies where a load is located in a different location with respect to the utility grid and the plant, where you have many plants close together. There are many ways of getting to the same system strength. So this system conditions that are considered in a product design doesn't necessarily cover absolutely everything that is possible, but it tries to cover the main characteristics of weak systems. Another comment related to this is that, as I mentioned, these turbines, so for example, the intention of a vendor is to sell 1,000 turbines, thousands of inverters per year. So it is the preferred approach to have configurations of settings for this equipment. So you will have, like, you could call one the weak grid configuration, another one the strong grid configuration, but you will try to avoid having to tune the controls of the converter for each project, because otherwise it gets pretty tough from the point of view of bookkeeping and the risk of making mistakes if every plant is configured differently. And then after this, like from the point of view of delivering these devices, there will be a project, and the project will go through an interconnection process. There will be some modeling discussion, and potentially there is some feedback towards how to configure the controls. Hopefully, for a converter control, that would mean that within the available configurations, you choose one so that you can meet the specific requirements. At the same time, you can deal with for example, the level of strength in the grid, since we're talking about that. For the plant level controller, it's different. The plant level controller, particularly for voltage. So on one side, it's different because you have one plant level controller per plant. You don't have 100 like you have turbines. But on the other hand, the voltage regulation aspects and all of that are more project specific, because the impedance seen by the controller is even more affected by the system strength in the utility than the converter control. So generally speaking, I want to mention this. So what is really affected when we talk about IBR stability? It's mostly about the converter control. There are some other aspects, but typically easier to resolve. And there are already practices in place by vendors to deal with low system strength. But you can see there are limitations to the approach too, because of how the cycle of product design works. So this slide talks a little bit about examples of stability risks. So there are two examples in this slide. On the left, we see the fast control interaction, and on the right, the voltage collapse. The one on the left shows, in the upper left, shows a very simple one-line diagram with 3 wind plants connected through a long transmission line to a bus that has an SVC. And from there, there are two outgoings that go to the rest of the utility system. And there is a particular contingency that when you trip one of those 2 lines, makes the system extremely weak. This particular case, composition ratio was around 1.2. So the system is very weak when you trip this particular line. That is shown in the upper right with the fault sign. There are 2 plots shown here. The one on the left is the response that you get if you tune your wind plant and the SVC for strong grid conditions. And you can see that there is sort of an oscillatory behavior. There's a fault and clear, and the system didn't recover. If you look at the details of the wiggles, there is a noticeable oscillation in reactive power around 20 hertz. If you look at the SVC that is not shown in this plot, you will find a similar oscillation. So there is a clear oscillation between reactive power between the SVC and the wind turbines. This problem was resolved by modifying the settings in the converter control, basically slowing down the voltage regulation. A similar effect could be seen by slowing down the SVC, the SVC voltage regulator response time. So this is an example of an interaction in the sense that you get the wind turbines interacting with the SVCs. The interaction is fast because you have sort of a 20 hertz oscillation of reactive power between the two. I would say that in the strong condition, so if you wouldn't trip the line that is stripped in this case, there is absolutely no problem. So there's no interaction. So the interaction has to do with how the injection of current on one source affects the voltages that the others see, sort of along the lines of what Nick described at the beginning of this conversation. But in this case, it's from one source to the other. And if the system is stronger, that interaction or that effect of the injection of current on one source to the other sort of goes away or is not as pronounced. The case on the right is a voltage collapse. But voltage collapse IBR flavor is quite different from the voltage collapse that the industry has talked about for so many years related to load behavior. So this case is not too different from the other one, although the characteristic voltage levels and stuff was different, but fundamentally you have a very large group of wind plants that are connected through a long transmission line like is shown in the diagram sort of in this upper center of the slide. In this case, we also have a remote fault that is clear, and what you see on the right are actually field recordings of this event that happened many years ago. So you can see the recordings. So on the right of the picture, there is one that says voltage. Those are voltages on the sending and receiving end. Sending end will be the voltage on the wind plant side of the long transmission line, and receiving end is in the opposite side. And then in the lower plot, you see the power. Both of them are kind of the same because the losses in the line are relatively low. So in this case, what you see is between the green markers, you see the fault time, and there is kind of an oscillatory behavior. That's actually not an oscillation, it's the effect of the unbalanced fault. So when you calculate the positive sequence quantities with the unbalanced fault, it looks like that. It's not really an oscillation, it's just a mathematical artifact of calculating positive sequencing quantities with several sequences. So you get a fault. As a result of the fault, the voltage drops on the sending end. The wind turbines see, and it's very common in the industry, that if the voltage magnitude is reduced, the IBRs will tend to reduce the active power. So the voltage magnitude is used as an indication that the system cannot really take the full power. So you reduce the power out of the IBRs, and that's what you see sort of on the second marker. At the time of fault clearing, the active power being injected by IBR is noticeably lower than before the fault. After that, there is a synchronization event. And then you can see that around 0.25 seconds in those plots, the voltages are relatively high because you're pushing less active power through the system. So the charging of the line kind of tends to bring the voltages high. And the power is relatively low. And at that point, the wind turbines decide to start increasing the active power. And from that on, you see a voltage collapse. So as the power increases, the voltages decreases, and it ends up collapsing the system. This collapse is very quick. I mean, if you look at it, it's 200 milliseconds, you collapse this huge system. The reason for that is that the speed of the voltage collapse is associated with the speed of the active power that is causing it. In this case, is the active power injection from the IBR, takes 200 milliseconds, and we see a voltage collapse in that time frame. If we think of the voltage collapse associated to load behavior that the industry has studied for so many years, that was low because the load, the active power behavior of loads is associated with a much slower dynamics. This plant has been, this was many years ago, it has been resolved by slowing down the active power recovery, and modifying the reactive power control so that there was enough reactive power to sustain the power transfer. But I thought it was good, or we thought it was good, to share this as an example of the type of problems associated with IBR instabilities. I would say the second aspect is not too much related to the synchronization challenge that Nick described at the beginning. It's described with a different aspect. The aspect on the left, the fast control interaction, has a relatively low relationship to that synchronization aspect, although that could have some level of impact. So these are two examples of instability that don't necessarily relate so much to the synchronization challenges. Those are also important challenges. I'm just highlighting that these are different to those. Now I'm going to jump to a different subject. I'm sorry, I'm jumping around about other aspects of the experience that we're seeing. I'm not going to try to use this to convey a message regarding what we see related to response time requirements of an inverter-based resources and system strength, and also the impact in bulk power system reliability. So on the upper left, you can see a very simple conceptual drawing of a block of a voltage regulator. So you have a voltage reference or variation of voltage reference on the upper left. Is the input to this regulator. The green box is the regulator, basically takes the voltage measurement or the variation of voltage measurement, calculates an error that goes through an integral action and calculates a modification of reactive power injection. This derivative of voltage with respect to reactive power is kind of you could look at that as the system reactance. So depending on how much reactive power, the modification of reactive power into the system and the system reactance, there will be a modification to voltage that ends up being the feedback to this voltage regulation loop. Right? So this is a simple, simplified version of a real voltage regulator. If this loop is relatively simple, if you calculate the response time of this loop, for example, the response time to a voltage reference change, it would be an approximation to that is the equation that is shown below the diagram, which is 3 times divided by the gain and divided by the system reactance. Now, this is very basic. I'm sorry, I know you guys have lots of experience. The main point out of this is that the response time of this regulator is not only a function of the setting in the controller, it's also a function of the system impedance, right? So now, if you look at the lower plot, so the plot right below that, in the x-axis, the system strength as 1 over the reactance of the system, the Thevenin reactance of the system as seen from the plant, and the y-axis, the response time, you see the straight line that is basically that equation that is there. Now, if this response, so what this is basically saying is as the system gets weaker, that will be, we move to the left in the plot, the response time gets faster, right? And if we make that too fast in real systems, we make it unstable because every system has latencies related to communication. There are delays that are not presented in this simple diagram. So if that response time gets too fast, it will go unstable. And that tends to happen for a voltage regulator when the system gets weaker. Okay, so that's one conclusion. From the equipment consideration point of view, the response depends on the settings, but also on the system strength. And the system strength gets lower for example, a voltage regulator, that response time gets really fast. If it gets really, really fast, at some point it will be unstable. If we look at it from the planning or requirement approach on the right, and I'm going to refer to sort of the right hand of this slide, we see, we try to here reflect the fact that the way system strength behaves in terms of the planning horizon is different now. So we were used to, or at least I was used to, systems that behave like the blue line. So as years go by, the system strength increases because we have more and more generators in the grid. But now, generators meaning synchronous machines in the grid. If we start thinking of a modification to that, where as time goes by, we have less and less synchronous machines in the system, or we have more hours where there are less synchronous machines in the system, probably with the years, the system strength is more like the green line, that it's going to go down as the years go by. And there is another version of this when you think about the ratio of system strength divided by the amount of IBRs that you get, and it's even worse, right? So the system strength particularly is relative, if expressed relative to the amount of IBR connected, is the number that will tend to go down with time. So now if we take the upper right plot and we combine it with the lower left plot, we get the lower right plot. I'm sorry, I have to speak like that because I cannot show you my mouse. So if we look at the lower right plot, that shows in the x-axis the years of operation of a particular plant or a particular system, and on the y-axis is the response time of some of the regulators there. So in a reasonable planning approach, you would have enough margin at the time you do the commissioning of the plant, and that's that dotted line that is presented with commissioning. You have enough margin to the instability such that as the response time reduces because the system strength reduces, you still have good margin and you're far away from being unstable. If on the contrary, at the time of commissioning, you try to make your controllers as fast as possible so that they are stable, but as fast as possible, then most likely what you will experience is what is indicated with the red line, which is in a few years, you're going to have to review these settings because this is going to start oscillating. So there is a very important aspect that we see the industry is having to decide related to this, which is you can ask how fast the equipment can move, but then it may not be the best idea to request all the equipment that you commission in your system to go as fast as possible, because the system strength are going to change during the lifetime of that equipment. So in that sense, it seems to be recommended to prioritize the reliability of the system by having good margins to points where different regulators may go unstable, over having the absolute fastest speed of response that you can get from the technology you are connecting. Next one. So another comment that is sort of challenging everybody in the industry, in different aspects, but everybody's being challenged by this. We are using, maybe I represent the company I work for, have been thinking about weak grid or low system strength in the context of the system that you see on the left. You have a plant that is new, you connect it through a long transmission line to a bulk power system, that the system of this connection is weak because this transmission line is very long or has a large impedance. And based on that, there are processes, the design processes are considering this to, and so all the converter control settings and things like that are designed thinking of this type of system. Now, what we're seeing more and more often is something like what you see on the right, where you can still see the new plant. I don't know if you can see it in between all the blue boxes. The new plant is still there, and the long transmission line is still there, and the bulk power system is far away. What has changed now is that you have a lot of other equipment, pre-existing equipment, that also has electronic control systems connected to the same point. And very often what we see is that the new plant that you connect maybe has fantastic grid-friendly capabilities and can withstand the weak grid and everything is fine. However, some of the pre-existing equipment is not, because it's older technology, is maybe different vendors, different design criteria. So some of the way that this challenge is evolving is that sometimes we see that dealing with weak grid is about dealing to the effect on pre-existing power electronic driven sources of the new devices, in addition to making sure that the new devices can withstand the specific weak grid conditions. And you can see how to reflect this in the design criteria for a particular vendor is also more challenging. So gonna elaborate a little bit on risk mitigation. So let's say you do find a stability risk. How do you mitigate it? And I think this was elaborated already, so I'm trying to avoid being repetitive. So the stuff on the left is kind of the typical conceptual discussion. So if you have a system that is too weak, well, maybe you don't need to do anything. Maybe it works. Maybe the inverter-based resources were designed to withstand that, and the rest of the equipment is designed to withstand that in a transmission system, and everything works. That's a possibility. In some cases, you may have to do something about it. So doing something about it could be related to transmission upgrades, usually not the preferred option. You could add additional lines to make the system stronger. You can try to go for a meshed approach where you can mesh the system so that the N-1 contingencies don't result in such a significant reduction of system strength. The use of series compensation is quite common in some markets around the world. Synchronous condenser was mentioned, that it solves the system strength. It may create new problems. SVCs and Statcoms help on one side, and there's additional power electronics that could interact on some others. And then you could have special protection schemes. I know it's something that I try to avoid because it takes a long time to get approvals for those, plus the operation of the grid make it complicated if you rely too much on special protection schemes to be stable. In addition to that, you also have control features in inverter-based resources. So it does happen that inverter-based resource companies may have features that are typically disabled that could be enabled to solve a particular problem that is observing a particular interconnection. And then another aspect that was mentioned before is the plant level control coordination that Jason described. So this is kind of the generic response to stability risk mitigations. What do we see in projects? And I'm sorry in this one that I realized that what I'm going to say is not so transmission planning related. It's more about what we see sort of in the street when we try to do projects in a way. So on one side, inverter-based resources are highly controllable. There is this notion that you can do absolutely everything with them. You just need to know what you need to do, and then you just implement it in the controller, and it would do it. So there is obviously limitations in that way of thinking, but it is true that they are highly controllable. And it's also the case that most developers prefer to do control modifications before they look into adding any expensive equipment to the system. So very often this is the first thing that gets looked at. Now, we do see that very often the solution to these problems, although they're technologically possible, take quite a bit of time. So these control interactions have a complexity that goes down to the lines of code in the controller of vendor 1 and the controller of vendor 2, and finding out what is specifically what is causing this and solving it could take quite a bit of time. So sometimes it takes so long, it would take so long to solve that, or there are some data exchange aspects that will be difficult to resolve, that this ends up not being the best option. So you do have this very flexible IBRs, but the complexity of the controls and how the different functions interact to each other result in a complexity that sometimes may create problems that are difficult to resolve. Regarding the potential issues that we see, so you have this discussion about large signal over small signal. So there is this aspect of weak grid that has to do with small signal, that if you have a very weak condition, you look at, for example, the synchronization problem that Nick was describing, and you make sure that for small variations, the PLL is able to track the voltage variation quickly enough that the injection of active and reactive current is such that it makes the system stable. There is that aspect with small variations. That is in fairly good shape. Typically, those are not the problems that we see. And this may be vendor specific, but generally most of the problems are related to large signal. So you look at faults, recovering from the fault, the over voltages that you may get after the fault. That is the type of problems that tend to be more limiting. The next point is related to requirements that demand maximum and fastest response. And I purposely left capability and is scratched because I think the industry tends sometimes, I'm not saying that it's the case of SPP, but in several places we see this confusion between asking for what is possible, what is this equipment capable, and then demanding to implement that in the project. So there are several systems where the maximum and fastest response is demanded to get the project connected. And then when you connect it, or when you study it in more detail, you realize that you need less responsive equipment or slower equipment. Otherwise, you get bulk power system type instabilities through the interaction with the grid. So this is an issue that is fairly common, I would say, at least globally. In terms of the specific of the inverter-based resources or other electronic control modifications, so slowing down the active power after fault is relatively common. It's related to the point I mentioned before, maybe. So slowing down the recovery of active power allows for the reactive power controls to ensure that there's enough reactive power to transfer the generation of the different sources during a contingency condition. So that it's a aspect. The reaction to high voltage magnitudes on recovery is quite important. So weak grids or systems with low system strength are characterized with high voltages on the clearing, like the recording I showed. That's very common. So how to deal with those high voltages in the sense of making sure that equipment is not tripped. At the same time, if you start absorbing reactive power to avoid the overvoltage, that you don't end up collapsing voltage. That balance of reactive power on the time of clearing is a very common subject of consideration. Then control adjustments in the new wind plant versus the old IBR plant close by is it's becoming a frequent subject in line with what I mentioned before, that you have a new wind plant, you look at the connection of the wind plant simulation environments and you see that actually that wind plant has no problems, but the previous plant does have problems, the plant that was already connected. So how do you deal with control adjustments to that? Do you do it in the new wind plant, trying to influence the old one? So that's a subject that's becoming more and more common. I'm going to skip the next one, and then the other one that is coming up very often is the slowdown of SVCs and Statcoms that already exist. It has been the approach in the SVC and Statcom industry to tune them very fast, like 50 millisecond voltage regulator response times, with the idea that the systems get stronger and stronger. So that's the best you can do. But now, because the systems actually get weaker and weaker, many system operators are finding themselves having to retune SVCs and Statcoms every couple of wind plants or solar plants that they connect. They have to retune them and slow them down because they're too fast for the new system strength levels.
Sebastian, you got 4 more minutes.
Thank you. With that in mind, I will mention briefly this. I showed this picture before, the one that you see in the center, where you have a number of wind plants with a long line and then a receiving end. The aspect of verifying in steady state power transfer capability is becoming, it is as relevant as it always was, if no more. So because IBRs don't have the transient stability challenges or the electromechanical oscillation challenges, you can push the active power closer to the nose of a voltage collapse point. Now, we find ourselves that it's very important to make verifications that the power transfer is possible in this steady state time frame before getting into fancy EMT aspects. So this is, I just wanted to highlight that this is true for everything. This is true for grid following, it's true for grid forming. It doesn't matter what source you got here. The equations or the laws related to power transfer through a long transmission system still apply. And so even grid forming has to comply with this. Just wanted to make that comment about that. And then I'll skip a couple of slides and move to the conclusion. So thanks for listening to, I think, a bunch of things that you probably already know. I hope that some aspects are interesting or useful. In general, there are several controls in inverter-based resources. Converter controls are the most affected, and we talked a little bit about how vendors deal with coming up with control algorithms and parameters of that ahead of a project. There are several forms of stability risk. Some of them are new. We talked about some of them. I also stressed this aspect of the difference between choosing a reliable power systems over fast inverter-based resource responses, and the importance of considering in your planning process and in the requirement planning, the system strength will decrease with time. It won't increase potentially. Also mentioned that the large signal performance aspect tend to be the more challenging to resolve, more than small signal aspects. And I share a couple of the specifics of project experience related to that. I had a couple of bullets, a couple of slides that I skipped in the interest of time related to EMT models. Maybe we get to those over the questions. Thanks for paying attention to me, and I pass it to Fred, or I don't know if there is any question that you want me to address, Debbie.
So Sebastian, there's a couple questions. One is, would reducing active power recovery after a fault cause other issues such as momentary cessation?
Not necessarily. So you could actually, the opposite is true. You could, if you do momentary cessation, you will be interrupting power for some time after the fault. Now, that's not the only way of reducing power injection. What I was referring to before was a control. So the inverter-based resource keeps controllability during and after the fault, but the way you recover power after the fault, you do it not too fast in low system strength conditions.
Thanks, Sebastian. Another question is, could IBRs create virtual system strength? At a high level, would this be similar to how they can create virtual inertia with some sacrifice of energy output, or are there other considerations?
Mm-hmm. Right. So that's a great question. So system strength you could see in two ways. One sort of related to voltage magnitude and reactive power, and one regarding angle frequency and active power. So on the voltage magnitude reactive power side, yes. And I would say some of the grid following IBRs do that in the sense that they have terminal voltage controls that have response times that are relatively fast, like 100 milliseconds or so. So you could say that in the time frame of the terminal voltage regulation, you are creating a virtual system strength. And that may be helpful for other IBRs connected close by. If you need to create virtual system strength in timeframes that are faster than that, then you may need to be looking at grid forming aspects. Regarding the angle changes frequency aspects of grid strength, in that case, you may need like the grid forming type of behavior to create that type of virtual system strength from an inverter-based resource.
Excellent. Thank you so much, Sebastian, and thanks for that presentation. With that, we're going to turn over to Fred Huang from ERCOT, who's going to explain ERCOT's experience in terms of the modeling and processes and what they've seen with IBRs and weak grids. So Fred, I'm going to turn it over to you.
Hi, thanks, Debbie. Before I start, could I check is my audio okay?
Yes, you sound fine.
Okay, thank you. So at my time, so good afternoon, everyone. And first of all, thanks for the opportunity for me to kind of share our experience and the practice in ERCOT, much related to how we interconnect the inverter-based resources and some experience and practice related to the weak grid. I think it's just like Katie pointed out in her open speech in the beginning, kind of similar to the SPP, we also have a lot of inverter-based connector ERCOT. So not only they can connect it in a very short time frame, but also we also get a very short notice before they come to us to connect. So that's really put a kind of relative challenge how to be more prepared and how to properly interconnect this resource into our system. So I think a kind of very high level overview for kind of my presentation today is to give a very quick brief update about in terms of the capacity kind of status in ERCOT on the inverter-based resource, mainly the wind farm and the solar projects. And also briefly talk about the interconnection process. In general, we have almost the same identical process for inverter-based resource and the conventional. Probably there are a few nuances I can point out today to share with the group. And as like the previous speakers kind of excellently provided a lot of coverage related to the stability and related to models. So I will also kind of share our current practice and the requirements on the dynamic model submittal for resource entity to provide information back to ERCOT and the transmission company. And lastly, we'll provide kind of share some examples and our ongoing practice, how we try to identify, study, and manage the weak grid in ERCOT footprint. So this slide kind of provide a very high level overview. So as of by end of this year, I think for the including the existed and the projects meet all the requirements likely will be online by end of this year. We expect to have approximately 46 gigawatt capacity. Again, mainly majority is wind projects, and we certainly see similar trend like SPP. I think moving forward, the solar project we expect to see a very similar trend like we experienced wind projects a few years ago. So as by end of this year, we expect to see 46, and within 2 years by 2023, like you can see the potential growth to our system could reach to 70 gigawatt by end of 2023. And most of the renewable projects in ERCOT or Texas is really in the West Texas, where with a lot of good potential on renewable resources. So on the other side, our major load center like DFW, Dallas-Fort Worth, Austin, San Antonio, Houston, they are at the east or like a coastal side of the Texas. So one of the first kind of system characteristic we are going to see a lot of change is going to see the need to be able to transfer a significant power through a long distance from West Texas to the load center. Secondly, I think because most of the load center are in the east part of Texas, so traditionally the conventional units, they are also concentrated or surrounded those load center area. So we have limited synchronous generators in West Texas. And under the high renewable output condition, and we also observe in real-time operations is we could have a condition such as the entire West Texas, we have only renewable resource available online when synchronous machine, they could be offline due to various reasons, including the market impact. So that's kind of a good kind of combination in terms of potential system like as weak grid characteristics. So a very quick update for the group is for ERCOT, as you may know well already, we kind of almost like one independent interconnection. We only have very limited around 1 gigawatt capacity back-to-back DC tie to our neighboring interconnections. So overall, we kind of manage the frequency, voltage, everything within ERCOT. So our current recorded high penetration from the wind generation perspective, the highest output was recorded on January 14 this year, around almost like a 23 gigawatt output. And from the penetration perspective, in terms of the load we serve through the wind generation, it reached to 66%, also recorded in March this year. So these slides kind of provide a very brief high-level overview in terms of the inverter-based resource interconnection process in ERCOT. So I think it's maybe similar to other regions with slightly different variations. Is kind of, we can consider very typical 5 stages. In one is the first stage, obviously, is a developer will make an interconnection request to ERCOT to initiate the whole interconnection process. And once we receive that request, the first one is to conduct we call it high-level screening analysis. And it's mainly steady-state analysis to identify, based on the proposed location, technology, and the capacity of the project, is there any potential transmission limitation to have that project to provide power to the ERCOT system. And after developer review the kind of screening study result, if they decide they want to move forward, then the next stage is going to the full interconnection process. And in that process, we will require a much more detailed analysis, including steady state, dynamic studies, short circuit studies, and the facility studies. And depend on the location and the technology, use the inverter-based resource as an example. If there are generators proposed close to the series capacitors, we require those projects need to perform a subsequent resonance analysis. And most of the time, those studies will require detailed Psk analysis. Also, we require all the projects need to perform and demonstrate they have a sufficient voltage support capability in the interconnection process that can provide adequate voltage support when they connect to the ERCOT system. We recently, probably 2-3 years ago, we implement a new process. We call it quarterly stability assessment. The purpose of this assessment is to identify any potential system stability constraints when we considering the existing resource and the new resource they are expected to connect to ERCOT within 3 to 6 months. And this is like a quarterly assessment. We do it every 3 months regularly. Just try to ensure after we go through all the interconnection process, we have extra check before they really sync to our system to verify and measure if there's any potential stability concerns. And if there is, then we will try to identify what is the mitigation plan we should consider or implement in the real-time operations. So among all these studies, I think that in general, we typically focus on summer peak, but for the inverter-based resource or the location we have concern from the high penetration over potential weaker grid perspective, we do require additional scenarios they need to be covered and included in the studies. A typical one we require is the high renewable scenarios, which we request the study need to consider the scenario where the projects at the nearby renewable, they need to be maximized output. Together, potentially need to turn off the nearby synchronous machine, and depend on the configuration, may also need to consider the impact of the major transmission outages to help to see if there is any potential weaker grid concern or system characteristics we need to be aware of from the stability perspective. So, and similar to like Kathy pointed out in the beginning, typically our observation is for IBR, they can go through our interconnection process from the beginning to the end just within 24 months. So kind of just repeat what I shared with the group. Not only they can come fast, they also give very short notice for us to be prepared. So this is a kind of ongoing challenge we try to address as well. So the previous one kind of mentioned through the process, it requires a lot of studies. And obviously studies are only good if we have good models and good information to start with. So in the last several years, from the dynamic model perspective, we went through several revisions, try to improve the process in the ERCOT region from the dynamic model perspective. So there's a lot of details behind the slides, and you probably can have a reference in the appendix. But I think here, try to give you a kind of overview about a summary of our current requirements from the model perspective. So the first one is all the IBRs, they are required to provide a PSSE and the Psk model to ERCOT. So that's a must requirement. So if IBR want to connect to ERCOT in the beginning, they not only need to provide like a PSSE or TSET model, they are also required to provide an EMT. In ERCOT, we use Psk, so they are required to provide a Psk models. And also, the resource entity, essentially is owner or the developer, they are responsible to provide the models. And not only the models, our current requirement also require additional testing and documents. They need to provide associated with the model together, really with the intent to provide a good, adequate, good quality, and possibly accurate model to ERCOT and our transmission companies together. So what kind of test and the document they need to provide it, I think we can try to simplify into 3 categories. So once they provide the model, they need to also provide the model quality test. The purpose for this one is just to ensure the model can work properly, provide an adequate response in the associated software, such as PSSE and Psk. So a typical testing include the flex start, which means the model can be initialized without a fault for a period of time. And also we request them to apply the test, such as the voltage test, like a small voltage step change, or large disturbance, such as VRT, voltage right-through test. And similarly, the frequency test, such as plus or minus frequency deviation, to see the model response on the frequency side. So from the weak grid perspective, we also require we call it like a special test. Is the model need to be tested under different system strength condition from the short circuit ratio perspective to examine the model behavior under different short circuit ratio. So currently we do not have a minimum system strength requirement, but this test will provide a very good and insight about the model behavior especially under weak grid condition. It really helps us as a study engineer and the planner or even the operation a better idea at what point the model and the software itself may hit a limit, such as additional tool and models such as Psk will be required to perform the analysis for that particular area. The second information and the test they need to provide it is a unit model validation. And this typically applied to the Psk models. So is when similar to the PSSE model, when the Psk model provided to us, we also would like to have some benchmark between the PSSE model and the real test, just to try to ensure the functionality and the way it model in the Psk can properly match the hardware performance in the laboratory. So this kind of a second test we require the owner or the developer need to provide it to us. The last one is more like a model verification. So we tried several ways. I think our current requirement is, in addition to the potential real-time benchmark through the event analysis, I think we try to think a slight alternative is we'll work with the vendor and the owner, try to ask them to provide some evidence about the key parameters in the actual control versus the associated parameters in the real models. So that can be as simple as they can take a snapshot or screenshot in the real controller as a key numbers and show that the number is actually implemented into the model provided to us. So this kind of 3 stages of the model testing and the validation, kind of through this process, that's how we consider will help us improve the models moving forward. So kind of few kind of keynotes I want to share with the group. So along with a lot of model activities, I think I just have some kind of highlights to share with the group. So in ERCOT, from the PSC T-set, like a typical phasor-based positive sequence model perspective, we do receive like a generic model or a user-defined model. So we don't have a requirement say the vendor or the owner must provide a generic model. So we are open to as long as the model is right. However, over the last few years, we observed the increased use of the generic model. And compared to our application at the potential weak grid area in our system, we observe, and obviously like Nick and others also cover this one as well. There is limitation for the existing widely available generic model can be used at the weak grid condition. So it's important to recognize where the limitation of the model is, and how we plan to apply the model into our studies. So I think our recommendation and our practice to our stakeholders is, if the model is, if they use the generic model to represent their inverter-based resource, I think we highly recommend, actually we encourage them, they need to check with the equipment manufacturers to be in the loop when they try to make the parameters and associated numbers to be used in the generic model. So that's kind of the observation we have, is the increasing generic models may cause the increasing numerical issues in the positive sequence simulation. And similarly, along with the model submittal and the tool testing, such as the model quality test I just mentioned in the previous slide. So we internally developed the tool and the process, and we actually share the tool with our stakeholders to help them to review and validate their model. And there is advantage on this one. So in the past, it's really they provide a model to ERCOT and the TSP, and the ERCOT and the TSP may be the first one to run the model into the simulation and start to identify a lot of issues. And we kind of circulate it back to the owner and the vendor, and go through several iterations, finally to nail down the model issues and update the model. It took a lot of time and effort. So what we try to do here is we request the vendor and the owner to do all those tests by themselves at the early stage, and we share the tool and kind of expected output or result with them. Then they have opportunity to identify those issues, if any, at the early stage, and resolve those issues before they come to us. So we really think that this is a process can facilitate not only ERCOT transmission company, but certainly it's going to be beneficial to the vendors and developers. So as I mentioned, we already share the kind of tools related to the PSC. And if the group is interested, you should find a link in the appendix in the end of the slides. And we are currently working on the tools for the Psk model quality test. And once we are shooting for to have the tool ready in third quarter this year. Once it's ready, we also plan to share with our stakeholders as well. So I think the last few slides just provide a very quick update and share our experience from the weak grid perspective. So the first example here is a very localized, is a wind projects, is actual wind projects connect to our transmission system. This example occurred about probably early 2012, 2013. So a very quick overview about this kind of special kind of example is we had a wind projects kind of connect to the 69 kV and through the two transmission line connect to the ERCOT main system. What happens at that time is we had a maintenance outage between bus 5 and bus 6. And at the moment, the project become radio connected to ERCOT through a single 69 kV circuit. And we also have a PMU at the POI location. So the top right is the actual PMU recording and during the high wind output condition. As you can clearly see, under that weak grid condition, really similar to Nick, Jason, and Sebastian mentioned it, because of outages, the system impedance increased. So the controller originally think is adequate for the normal system condition becomes too aggressive. And under the high wind output condition, we start to see the undamped and even negative damped oscillation, and eventually the wind project trip. And it tripped several times after we start to put into the investigation, and kind of the whole weak grid issues really start help us get a lot of lesson learned through these particular examples back to early 2012, 2013. So the key lesson learned that we have here is one is kind of really repeat what all the previous presenters covered. The first one is we start to recognize the model and the tool adequacy issue. So the projects went through an interconnection process, and at that earlier times, we did a SCR test, and kind of to mimic what Sebastian highlighted, a single SCR test for inverters, our finding is it could provide a very optimistic result if we have nearby projects we do not take into account. And this is a typical example. So at our early time, when we connected the projects, I think we reviewed the SCR at the POI, and may not properly take into account the neighboring projects' impact. And this is where we start to develop the WSCR, which I will mention later for ERCOT application. And the second one is similar, is the controller become very sensitive when the system is at a weak grid condition. So how to properly identify and properly tune it become kind of one of the challenge and the practice we start to adopt. So there are many mitigation plans or options can make the project stable. And I think one very quick one we identify in real time when this event occurred is we just reduce the output. So by managing the inverter-based output at a lower level can help stabilize the system response under the weaker grid condition. And the second one, obviously, is the tuning. Is if you are aware of the condition, you may have a way to properly tune the projects to have reliable response. But there's a caveat, like Sebastian mentioned, if the system continue to evolve, we kind of need to have a process to regularly review the controller in the area, and may need to tune as necessary over the times. And then finally, there's multiple ways to improve the system strength from the planning perspective, or if it can be implemented, such as condensers or new circuits, or various way you can find a way to reduce the impedance.
Fred, you have 4 more minutes.
Thank you. So the last example is kind of ERCOT panhandle example. So the previous one is a localized one. I think here, once we start having more inverters connect to, I think we start to observe the weaker grid challenge can start to also expand it to be like an area or region-wide issues. So panhandle is a very typical example we are addressing right now. Is panhandle is like a northwest corner of Texas, which we have only transmission circuit 345 kV mainly, and the inverter-based resource. So we have almost zero load and zero synchronous machine in this area, and transfer a long distance to the load center like east of Texas. So like today we have more than 10 gigawatt inverter-based resource connected to panhandle and the nearby area. So I think how did we identify is a potential weaker grid? Like the first one, most of likely we observe in the PSC simulation, when you start to see a high frequency oscillation over numerical issues, that generally is a hint that area can be weak. Or if we apply the fault, you start to see the overshoot of the voltage right after the fault start to increase. That's also another hint that the system is getting weaker. Or you can just simply run a short circuit analysis to look at the short circuit current versus the capacity in the area. That may also provide information of potential weak grid condition. So our practice right now is in panhandle, when we identify it's weak, we put the condensers in. So we did put add the two synchronous condenser in panhandle to provide the system strength and also provide the dynamic rated support. And really to echo what Nick mentioned in the beginning, when you put the condensers in, I think the associated stability related to the synchronous condenser, it need to be checked before you implement the condensers to the system. And then other possible way, similarly, you add a new circuit, and again, similar is a controller tuning. It's possible can further make the system stable, but we do see from our perspective, the tuning and the coordination could become more and more challenges compared to other options, just because of the numbers of entities need to be involved to make that one happen. So I probably will skip this one, but I think as a high level, what we did in ERCOT is since 2016, we start to perform a Psk analysis just because we identify the weak grid. So for the region like a Panhandle and now even the South Texas, where we also have a large amount of renewables, we start to perform the Psk analysis. And I think as most of the group may be aware of, the Psk is more detailed analysis. So really the challenge is really time consuming and it's a really complicated process to do the analysis compared to the PSSE. So just give you a quick example. In 2020, when we performed the Panhandle study, in Psk we modeled more than 500 buses, and we used like a parallel computation to make it happen. Even so, to run one contingency, it took us 2.5 hours. So it's quite a big challenge to be able to potentially consider this can be an operational tool moving forward. However, we do see the trend there. So obviously, the tool improvements or something new will be needed to fulfill what we can continue to do the assessment. So I think this message kind of show, this slide just show the various tools we use in planning and operations to manage it related to the stability and the weak grid. So we have Psk, we have PSSE, we have VSET in planning we typically used. We also have weighted short circuit ratio we used. It's really try to help us to identify the potential weak grid condition. And in real time, we also have real-time WSCR. We have stability, and we do it offline analysis, and we have online VSET, and we currently is implementing the online TSET right now. So before I go to the slides, I think one caveat I do want to share with the group, the index in terms of the SCR or any other index like we use in ERCOT as a WSCR, when we decide to use a WSCR, we ran a lot of Psk studies just to make sure the WSCR index can be properly applied to a particular region like a Panhandle. And our observation was the WSCR and the threshold is likely not applicable to any other region until you do the detailed analysis. So that is something we also have a challenge to try to see, can we have a universal or a potential good index can be applied system-wide, and that's something we are working on as right now. Sorry, I went through very quick, but in short, I think from the inverter-based interconnection to ERCOT system and our kind of observation, to summarize it is, with more inverters connected to our system, and because the concentration of inverter base in West Texas and South Texas, we do observe the increasing stability and also the system strength challenges when they connect to the grid. So there are various kind of sub-bullet here point out, which I can already cover in the previous slides. So I think the one we really learned a lot is early communication and the coordination is always better, and really can help us to better and more smoother to integrate the inverters. So that will conclude my update to the group. Thank you.
Oh, thank you so much, Fred. That was extremely helpful. There's a couple questions. One is, so I think it was slide 7 in the weak grid analysis. The oscillation of the wind project due to the fault on the 69 kV line, did that show up in the initial dynamic simulation study?
Thank you for the question. So I probably just want to make a clarification. I think this can occur without a fault. So I think what happens here when we have a maintenance outage, and just you don't need to have a fault. It's just something potential trigger, like a bank switching. You can potentially trigger this oscillation. So in our original analysis, we did not observe that one, and that's I kind of skip it. Is the lower right. That's where, after we realize our model and the tool challenges, that's how we work with the vendor to properly integrate that features into the PSC model and also Psk and help us to identify moving forward.
Great, thanks. Another question, what field tests are required for plants at commissioning or on a periodic basis? For example, are there required tests of the IBR settings? If not, how do you diagnose misbehavior? Would PMU data address that need?
Yeah, thank you. So I think our intent for our proposal is not to require a lot of the actual test. That's our intent, in addition to what they are required as a typical commissioning already. So our intent is try to through the unit model validation, which is a comparison between Psk model and the actual hardware test. And it can be done in the laboratory. So the purpose here is to want to make sure the PSC model include the right functionality to represent the actual hardware, regardless of the settings. Then when we come to the model verification as a third stage, all we need is, do we have the right information in terms of numbers into that model? So combine these two together, that's how we kind of find another alternative to say this model is good enough compared to you can actually benchmark the real event. So that's kind of our mindset when we kind of revise our process.
Okay, great. Thank you, Fred. At this point, I'd like to open it up to if folks want to raise their hands and unmic themselves and ask more detailed questions. And I guess I'd like to ask the other presenters if they could, they can show their videos and we can have a bit more of a discussion now. And while we're waiting for questions, I guess I'd also like to give the speakers a chance. I know that we did this, everyone was really fast and stayed on time, that's great. If there were things that you didn't get a chance to say, or if there's points that you think need to get made that weren't made, this would now be a good time to do that. Or if you want to respond to someone else's presentation. So maybe I'll just start with Nick, since you were first, if there's any last words that you wanted to say to folks. All right, I don't see Nick. Oh, there he is. Oh, but I can't hear him. Nick, I can't hear you. Let's see. No, still can't hear you. It doesn't show that you're muted. It must be a mute on your end.
Can you hear me now?
Yes, yes, yes.
All right. All right. My headset decided to go on strike. As my colleagues here got deeper into the reality, my high level talk sort of hopefully made some more sense. And, for another day, it will be very interesting with this gang and to see how the industry goes. You saw I made quick references to grid forming inverters. We didn't spend a lot on that today, rightly, because that's to some extent the next frontier. But those are, whatever that means exactly. So I want to make sure that the audience understands that there isn't like a thing that is a grid forming inverter. We're far as an industry from that, but machines that have the attributes that will overcome some of these weak grid and other stability issues are things to stay tuned for. So we can do that as we move forward.
Great, thanks. Jason, did you want to?
It was a great discussion, and particularly as we got more into the details, segueing from what Nick said to what Sebastian and Fred said. I want to kind of point on a question that came up in the chat that Deepak asked that I think is a very relevant thing. In the interconnection process, obviously, trying to get what's actually installed or what's actually needed in the field into the models to evaluate the behavior and the risk is the name of the game. And that's kind of why we pulled on, well, what model do you use when? And particularly for issues like plant level coordination or inverter level interaction and coordination, choosing the right parameterization of the models, as we've been saying, is very key. And doing that upfront as soon as possible is definitely it makes the whole process very much easier. And in engaging and involving the manufacturer, engaging and involving the grid company with the developer all together to help identify those needs if there is a weak grid or if there are other stability concerns as soon as you can is definitely, it would highly help the process. So just wanted to reiterate that, and thank you, Deepak, for the question. I think, as usual, it's spot on.
Great, thanks, Jason. Sebastian, did you want to add anything?
Sure. A comment that I would have for considering that SPP has so much experience and they're looking at what they may want to do differently moving forward. I think it's a challenge that we see in general globally in places where they already have significant percentage of IBRs is you clearly see the need to maybe improve processes around models that reflect the equipment better. I think the description from Fred is great about how ERCOT is looking at tests and models and improving the way the confidence around the models in different operating conditions and potentially wanted to verify more performance aspects. There is clearly a need for that. Now, the risk is to add a lot of process around things that are not so valuable from the point of view of reliability. And it's not that I know how to do this, I'm just stating what I see. There are some places globally where the processes have created many steps related to model verifications that at the end do not have a significant impact in reliability. And there is a lot of focus on the process, and you could forget the main objective, which is making sure that as you incorporate technology to your grid, that the grid remains reliable. So, and that's a balance. I don't want to claim that I know the answer what the balance is, but it's important to keep in mind what is important and what is interesting, and it's to some extent relevant, but it's not as important as other things. That balance is really challenging. And I guess I just want to highlight that aspect.
Great, thanks. And Fred, I'll let you follow up with any points you wanted to make, and then we have a question from William.
I think probably just in short, what we see is we see the increasing need of the Psk analysis, and obviously the model becomes more critical, and we do see more challenges, and I know the group is very aware of it, but our experience certainly tell us even the Psk model, you still have a lot of issues inside. You may need to figure it out before you can really use it. It's not that you get a Psk model, you can do everything right away. But this is something I think we continue to try to find a way to improve in our process and to see how we can make the whole process better. On the other side, the Psk studies we are facing right now is really the tool adequacy and the efficiency, like Jason pointed out in the beginning. Moving forward, PSC is still our main planning tools, and we start to see the need to increase study the Psk. And ultimately, all those resources will connect to real time. So how we can manage that one properly and still handle a lot of difficulty efficiently, that is the challenge we kind of need to address. And actually, I'm looking forward to see the feedback and we can learn from SPP as well. Thank you.
Great, thanks, Red. William, do you want to unmute yourself? I know you've got a question on grid forming IBRs.
Yeah, I was just, you know, with the presentation there from Nicholas at the start, he kind of touched on grid forming and grid following. And yeah, I think you piqued my curiosity there on the grid forming technologies. I don't think I had you know, that curiosity resolved. And so I was just kind of wondering, you know, what makes a grid forming resource, and you know, with the existing facilities that are out there, you know, can they be easily upgraded once the, you know, whatever control system is required is designed, or what does that look like?
Right. Well, I'll give you a sort of the expected answer, which is it depends. But so there are design issues that go with making it an inverter grid following or grid forming. The relatively short answer is that the ability to do that for wind, which is your primary resource, appears to be sort of, it's possible, but, and there's a whole bunch of buts that make me believe that it won't become widespread practice. It substantively changes the mechanical in particular, but electrical stresses on the wind turbine to have it grid forming. It again, recognizing that grid forming is kind of a bucket of behaviors that isn't specifically one thing, but it tightens the mechanical coupling to the grid, and therefore there are stress issues. There's also rating issues. So grid forming tends to be a little more current hungry, and the way the devices go into current limits is different. So for wind, the answer to that question is going to be, I don't see it happening in a widespread fashion. Solar's a little easier because there's nothing moving. There's some practitioners, of whom I personally am becoming a member, that believe that the time for starting to require grid forming capability from energy storage, specifically batteries, is upon us. So don't make the mistake of thinking that if somebody puts a battery energy storage system, you've got grid forming necessarily. That in general is not the case. You need to ask for it and specify and say what it wants to do. But with batteries, grid forming is in some sense more familiar ground. It's already possible. And I'm starting to join a growing chorus of people that are sort of the opinion, when you put in battery systems, make them grid forming and start asking for that right away. Sorry, it's a pretty long answer. Hope that helps.
And do others want to respond to that question? Or do you want to mention some of the grid forming battery systems that you've worked on?
I could add a little bit to what Nick said. So from one aspect to the upgrade is the consideration that the lifetime of the products in the renewable area are short. So if you have a turbine that has been connected for 10 years, there is probably not a team of engineers working in upgrading or keeping up with the details of that converter control. So vendors would tend to be adverse towards doing upgrades of relatively old technology unless there is a significant market for it. And I'm not necessarily saying that for GE. I think in general is an aspect. And then, like Nick said, one of the aspects of performing a grid forming function has to do with a fast absorption and injection of active power into the grid, faster than what IBRs do now. So if that requires to modify the hardware in the system, and this upgrade is not only a software change, then even more so, it will become challenging. And I agree with what Nick said. There are already commercially available grid-forming systems with batteries. But I don't think the industry is fully utilizing.
All right, thanks, Sebastian. Are there any additional questions? If you just raise your hand, or you can unmute yourself, I think that should work. I guess while we're waiting, I know that one of the things that we were talking about when we were planning this was sort of the idea of how much you focus in on. Oh, Casey, I'm sorry. Did you have a question you wanted to ask?
Yeah, actually I do. So when we started out with a lot of wind, we had a lot of non-dispatchable variable energy resources, and we spent almost 8 years creating policy to help address moving towards a dispatchable fleet. And so now moving forward, resources must be dispatchable. Something that Nick mentioned and others, it gives me question on if we know that we need to have grid forming IBRs moving forward. The concern I might have is that we have a lot of batteries or solar farms that are grid following, and then what is the investment, or is it even possible, as we just discussed, on upgrading those resources? And so the question I guess I have is a couple of questions. One is, do we have an appreciation for what the cost difference is for the capital investments for developers if we create a policy moving forward? And, you know, just to the ERCOT situation, I mean, ERCOT being their own interconnect has always, to me, been a blessing and a curse. It's a blessing because you can absolutely have more defined studies because it's its own interconnect versus some of the blessing that SPP has is being connected to the Eastern Interconnection. But one of the challenges SPP has is, since we are part of the Eastern Interconnection, it's a little bit more difficult to prove out certain needs that maybe ERCOT could prove out for creation. So I guess it's twofold. It's one is, do you guys have a appreciation for what the cost difference might be, and if there are any suggestions or things that we may look at as SPPs and SPP staff and SPP members might look at to create policy change prior to the interconnection of a massive amount of, let's say, ESRs. But again, we're trying to develop this stuff to where we're not trying to increase cost to increase, but I personally would not like a lot of ESRs to connect and then we find a problem.
Let me start, and then I'll let Sebastian kick in because he's always a little more practical than I am, Casey. But those are great questions. And one of the things that's going on in the community that's trying to answer this, what do we want from grid forming, and what can it do, and very importantly, what can't it do? Because we all wince at the idea that grid forming makes all your other problems go away, because that's certainly not the case. But there's some good work being done that's asking the question of what fraction, just pick a circumstance that you guys are getting close to. Sometime down the road, you got an hour of 100% IBR in your footprint, just for the sake of discussion. What fraction, there's a lot of research being done to ask the question, what fraction of that resource needs to be grid forming? Because the answer isn't not all, the answer we're pretty sure as an industry isn't everything that's running needs to turn into grid forming. That's a work in progress. There seems, and I love rules of thumb. There's starting to sort of be a emerging pattern of three parts grid following to 1 part grid forming. I know, obviously you can't take that to the bank. Siemens did some really clever work where they're pushing the envelope really hard, where they took, and this is germane to the previous question, Siemens actually retrofit the controls of commercial present generation grid following wind turbines, big ones, 2, 3s, in Scotland. And they went and they made them grid forming, and they did a whole bunch of tests. And they came back partly with those answers that I said, which is you got to be careful because they can't push it. Siemens documented all that, but they did a bunch of really cool experiments, and they were successful with big footnotes. Don't try this at home. It's like watching TV. They successfully ran an electrical island with 20 to 1. 1 part grid forming, 19 parts grid following. Nobody's saying that you can do that. So that's a piece of the puzzle. The other piece of the puzzle on cost, I'm going to dissemble a little bit, but one of the things that we worry about as a cost component is the mechanical stresses and the current rating, right? One of the reasons why we have grid following inverters is current rating equals cost. It's a real, there's a very strong correlation there. And grid following technology of the current state of the art uses the current capability of the machines and shares the burden between many turbines. As you said, you got 14,000 of them, and they don't really fight very much. That's partly by virtue of them being grid following. When we figure out exactly what we want from grid forming, it's likely to affect the current ratings. And that's kind of a work in progress right now. You can't, people talk about virtual synchronous machines. I don't know if you've heard that language. Say, well, just make it look like a synchronous machine. Well, synchronous machines got, what, 3 or 4 per unit short-term current rating? That ain't happening. The economics are not going to drive inverter ratings that high. So part of the debate, part of the investigation, I shouldn't call it a debate, is how much current rating do you really need? Because that's going to turn into a cost term. So I'll stop there. We're probably not talking about doubling the cost. We're probably talking more than noise. Sebastian?
Yeah, so my comment, I have a couple of comments. So one is, to establish the cost difference, you need a number of prerequisites that are not there yet. It depends what you're looking at, but in general, they are not there yet. So one of them is to clearly specify the performance you want from grid forming, so that then you can define a price and compare it with the price of not having it. One of the challenges that the industry has now is to clearly define the performance. And that performance could drive difference in cost. Like if, for example, the experiment that was described by a different vendor from Nick is actually not a product that necessarily does all the grid forming activities, all the grid forming performances that are required for a number of contingencies. It was great to characterize what you could do and put limits on the different performances. Now, if you want to have that available for our contingencies, or you want to have more than that, then that product is not there yet. So there is not enough, and it's actually very complex to do, is how do you define the necessary performance of grid forming? I think the industry is still figuring that out. Figuring the price difference before that's figured out is particularly challenging, and this, I guess that comment is particular to wind turbines. And yeah, particularly for wind turbines. I think on batteries, it's probably possible to answer the question of what is the cost difference, and I suspect that it's not that much. And that can be answered because there are vendors that commercially offer this. I'm not able to say a number that's not the part of the business that I'm involved with, but I suspect that the difference is not too big for battery systems. But I do expect it to be more significant for wind turbines. And I do think that the discussion about the performance difference are going to affect the cost for wind turbines than it will for batteries. So, sorry, it's a very long answer for my point too.
No, thank you both. Thank you both. That was very helpful, and I did want the members to listen to that answer as well, because there's going to be more to come. And Nick, you kind of mentioned it, that the proper mix is going to be challenging. You know, it's one thing to make a policy on all new generation, but it's another to try to be tactical on exactly what the right mix is, and imposing some of those requirements on developers on the front end, and understanding what the region needs at the time. And so more to come there. Thank you.
Thanks, guys. I think there's a question from Mallory Manoni. Mallory, if you want to unmute yourself, you can ask your question. All right, I can't hear Mallory. Mallory, I guess if you can't unmute, you could try typing it into the chat.
Can you guys hear me now?
Yes, yes, we can hear you.
Excellent. Excellent. Thank you guys for your presentation today. Really helpful. Enjoyed hearing from all of you. I just had a kind of a more high level question back to almost the initial presentation by Nick, relevant to the SCR and the weighted SCR. And I, as a background, am fairly involved in the generation interconnection studies of obviously IBRs. And I'm more wondering, how do you assess an individual IBR when you've got several others nearby that might be on the existing system? And how do you try to classify a mitigation or an adverse impact of a single IBR that's happening because of weak grid? Like, I've seen cases where maybe my SCR is near 5, so not really the ratio that we've discussed in the presentation today, not in that 1 to 3 where you've really identified a true weak grid, and then a new IBR is coming in and we're seeing the kind of signals of stability limitations, the crash simulations, the high frequency oscillations. Does that just warrant a full EMT study at that point, or is there anything that you can do in that high level PSC simulation to kind of pull out one inverter's issue from another, or do you just kind of have to dig in straight to that EMT analysis at that point?
I am going to punt that to Fred and Sebastian, who live in that particular uncomfortable world all the time.
I can offer a comment. Fred, do you want to go first?
Okay, so I think to share what we typically do here is in the interconnection process. As you point out, in ERCOT they are required to do the PSC analysis. So there are a few hints. It's possibly we try to use as a potential indicator. So in the PSC analysis, if we do see the stability analysis, if we do see the potential the numerical issues or high frequency oscillations, that it kind of typically is a hint. That area, especially for the study engineer, should be recognized that the overall area. So that's kind of a hint to show the potential weak grid condition. We do, as I kind of shared earlier, we try to stay away from using the SCR for a single point, because what we observe is, especially in a cluster or area where it's really dominated by the inverters, a single SCR at the interconnection bus typically provide optimistic result. So you may find the SCR is like a 5, even 10 potentially, but when you properly include all the nearby together, the actual SCR is relatively low. So we actually try to stay away from use SCR any further. Another potential is we do a short circuit analysis, and we try to identify what the potential lowest short circuit current in the area. And it can be down to the engineering judgment, like where you know the total capacity in the area, you know what's the potential lowers short circuit current at the major transmission bus, kind of do some simplified WSCR calculation, not a particular threshold, but we will see the trend, and that's how we decide where we want to do where we need to do the Psk analysis. So it is not defined the black and white criteria, but that's kind of the practice we currently use to determine when to need to go into the Psk if necessary.
I second everything that Fred said, and I would be even very specific. If you have more than one source, or more than one IBR plant, you should not use SCR because it's too optimistic. Using WSCR or CSCR or other form of SCR where you estimate the short circuit ratio of the collection of IBRs in the area is more conducive, and it has limitations. But definitely, I would recommend not to use SCR if you have more than one IBR plant close by, because it's going to lead, like you said, it's going to give you the wrong impression that everything is fine most of the time. In general, I think it's good to think about these SCRs. I think the naming that the industry gave to them is really misleading, because we talk about it's a short circuit ratio, and it gives the impression it's related to short circuit. Fundamentally, what you're trying to do is try to find some indicator that gives you an idea of the impedance seen into the grid by all the inverter-based resources in the area. So when you add a resource, you want to see what is the impedance or the system strength seen by the resources that you already had, plus the new one into the grid. It's a single indicator for all of them, more than the new plant in isolation. So I agree with what Fred said, and I think I agree with the tone of your question, where you see that SCR alone is not a good metric. It is not. It's very optimistic.
Thank you for that very much.
Great, thank you all so much. So I'm realizing it's 2:30, or I guess it's 3:30 your time, and we're going to need to wrap up here. I wanted to say that if people have feedback, they can email either myself or Casey at SPP. And we had planned for this to be one of two workshops. We had planned to follow this up with a workshop that was either actually more of a system level workshop that we wanted to hold later this year. And if you have feedback into what you'd like to see in that, we would welcome your input. I would like to thank all of the speakers for donating their time and effort to really share with us all these experiences and lessons learned and their knowledge base. So a huge grateful thank you to the speakers for helping out. And Casey, I don't know if you'd like to make any closing remarks, but if you would, that would be fine.
Yeah, just thank you again for attending, and very good questions, and I really appreciate the speakers. I think this was very valuable. As you mentioned, just repeat, you can send an email to myself or Debbie or both for any feedback you had on this workshop or any suggestions for the next workshop. Thanks again.
Thanks. Oh, and I forgot to mention, we are going to post everything on it'll be on the E-Cig website. I'll send you a link whenever all the presentations get posted, so you'll have access to that and to the recording. But thank everyone for participating, and thank you again to all the speakers.